Why do some regions of the universe behave as if something is watching them back? Not metaphorically, but through patterns of light and motion so strange that even seasoned astronomers step away from their screens, unsure of what they're witnessing. Some cosmic structures flicker like pupils responding to light. Others pulse in slow, rhythmic waves, as though the void itself were breathing. And every time scientists try to explain these shapes, the explanations crumble under the weight of deeper questions. Welcome back, traveler. Tonight we drift through science. You're here in the quiet, maybe lying on your bed, maybe resting on a couch with the lights low and your thoughts finally loosening their grip. This is the kind of stillness where the universe feels close enough to touch. And if this gentle journey helps you unwind, leaving a like and subscribing keeps this sanctuary glowing softly for nights just like this one. If your mind feels heavy, if sleep has been distant, or if your thoughts are tangled in the events of your day, you belong here. Some mysteries are complicated even for the people who dedicate their entire lives to them. You don't need to catch every theory or remember every detail. Let the questions drift around you like faint starlight, soft, harmless, and content to simply exist while you rest. Tonight, we'll wander into the strange corners of the cosmos where beauty and impossibility meet. We'll step inside nebulae that behave like living creatures, explore voids that whisper through gravitational fingerprints, and linger near structures whose symmetry is so precise it borders on intentional. And along the way, we'll visit observatories where exhausted researchers rub their eyes, replay the same images, and realize that what they're seeing doesn't fit into any model they've ever trusted. So settle deeper into whatever holds you. Let your breathing slow. Let the room darken into something safe, and let your curiosity stretch out without needing to grasp anything. Tonight we walk toward the kinds of questions that don't ask to be solved, only witnessed. And somewhere in that quiet space between knowledge and wonder, the first anomaly begins to take shape. You're floating in the quiet above a sprawling nebula, the colors shifting like slow breath beneath you. The air around your imagination feels cold and vast, but not unfriendly, as if the universe itself were inviting you to peer closer. In this drifting space, one particular region glows with a faint pulse, not random, not chaotic, but almost deliberate. The flicker doesn't match anything you'd expect from gas clouds or dying stars. It repeats with a rhythm that seems to hover just outside human intuition. Scientists first found this anomaly in data from a deep sky survey meant to map star formation. The rhythm caught the attention of an intern who thought it was an error in the software reading the photons. But when senior astronomers checked the raw observations, the flicker was still there, steady, repeating, and unsettlingly smooth. It was too slow to be a pulsar, too structured to be noise, and far too consistent to be a coincidence of overlapping sources. You're drifting closer, watching the light expand and contract like a quiet heartbeat cast across light years. It's so faint that you almost feel it rather than see it, a distant signal woven into dark matter's endless fabric. You sense the immensity of it, and at the same time, the intimacy, like something unfathomably large expressing itself in a whisper. The darkness around it becomes a kind of canvas, letting the pattern stand out with delicate clarity. Researchers measured the timings and discovered something unnerving. The intervals between pulses weren't identical. They drifted by fractions of milliseconds in a way that didn't correspond to any known physical object. Variable stars change brightness, but their periods come from internal processes. This pulse behaved as if responding to something external, nudged by an invisible hand. It wasn't impossible, it just didn't resemble anything that belonged to stellar evolution. In one of the observatories analyzing the data, a scientist printed the pulse sequence and taped it to her wall. She traced her finger over the peaks, trying to find a mathematical relationship. She found none. Instead, what emerged was a gnawing feeling that the signal wasn't random, but that its logic existed in a framework humans hadn't yet imagined. She double-checked every calibration, reinstalled every driver, even cleaned dust from the optical path. The pulses persisted like an unanswered question. You imagine yourself lying beneath the flicker, the way a traveler might lie under a campfire's glow. But this light isn't warm. It's ancient, stretched thin by the expanding universe. Yet something about it feels alive in a quiet, indifferent way. It doesn't care about being interpreted, and perhaps that's why it unsettles you. The beauty comes wrapped in a kind of cosmic detachment, reminding you that the universe often reveals just enough to confuse, not enough to comfort. Spectrometers revealed that the flickering region lacked the usual emission lines expected from gases interacting with starlight. Instead, the wavelengths had subtle distortions, as if the photons had been bent by a gravitational field that didn't appear in any mass map. Something invisible was sculpting the light. It wasn't strong enough to act like a black hole, nor faint enough to be dismissed as dust. It was the gravitational equivalent of a footprint with no visible creature. In a dim control room, a graduate student zoomed into the region and noticed tiny shifts in the position of surrounding stars. They were wobbling, just slightly, on timescales too short for celestial mechanics. It was as if the fabric behind them was trembling. She replayed the footage again and again, convinced her coffee-induced fatigue was inventing things. Then she called her supervisor, who stood silently for several minutes before whispering, "This shouldn't be happening. You drift around the anomaly, watching the stars distort and relax like reflections on rippling water. The wave moves without a source, a soft trembling that shouldn't exist in the vacuum of interstellar space. You feel yourself leaning into the mystery, as though listening for the faint sound of it. There's no noise, only the suggestion of movement that could vanish the moment you think you understand it. Astrophysicists attempted simulations to reproduce the phenomenon, adjusting parameters for hypothetical particles, exotic fields, or unseen companions. None matched the observations. The models either collapsed into chaos or produced steady, predictable pulses, nothing like the trembling heartbeat observed. It was as if the anomaly were obeying rules that contradicted the known behaviors of matter and gravity. Observers at the ALMA array pointed their antennas toward the region, hoping radio waves would reveal the nature of whatever lurked there. Instead, the readings fluctuated between near silence and faint static with no recognizable pattern. Radio silence isn't unusual in space, but silence that changes unpredictably is. It suggested something interacting with the electromagnetic field in a way no known object can. You picture the scientists leaning over their keyboards, tired but captivated, while you float in the quiet of imagined space. The flicker becomes a kind of cosmic metronome guiding your breathing. It slows you down, draws you inward, and leaves you wondering whether the universe is expressing a rhythm too subtle for equations, but not too subtle for human intuition. Sometimes, understanding begins as a feeling rather than a formula. Deep learning algorithms were trained to identify the source, comparing it to hundreds of thousands of known cosmic objects. The system misclassified it every time, first as a pulsar, then a quasar, then an artifact. It couldn't settle on an answer, because the anomaly overlapped categories that shouldn't overlap. Even artificial intelligence struggled to fit it into the universe's existing vocabulary. In meetings, astrophysicists sketched possibilities on whiteboards. Exotic particles interacting with dark matter, a rotating structure hidden inside a dust cocoon, or even a fragment of space-time behaving like a resonant chamber. The theories grew stranger with each attempt, stretching physics toward its breaking point. When no idea survived peer review, the mood shifted from frustration to awe. The anomaly wasn't just unexplained, it was suggestive, like a clue dropped by the cosmos. You drift a little farther away, noticing how the nebula's colors seem to hush themselves near the flickering region. The dust clouds thin, as if giving space to something delicate. The universe doesn't usually make room for anything, yet here, emptiness gathers around the pulse with gentle reverence. You feel it tugging at your imagination, hinting at a structure behind the illusion of chaos. Further analysis revealed that the flicker's energy output subtly changed depending on the angle of observation. Something about it responded to perspective, but cosmic objects aren't aware of being observed. Their light doesn't adapt to the viewer. This variability should have pointed to a rotating structure, yet nothing rotated. The effect was reminiscent of gravitational lensing, except there was no lens. In one late-night session, a physicist stared at the data and realized the pulse intervals resembled interference patterns, like waves overlapping in a place with no medium. But interference requires two sources interacting. Here there was only one. Unless, of course, the second source was invisible. Not in the sense of being faint, but in the sense of not existing within space-time as we understand it. You consider this possibility while floating in the imagined stillness. The pulse feels like a message, not because it communicates anything, but because it repeats with patience, a rhythm with no performer, a heartbeat with no heart. Your breath synchronizes with it for a moment before you remind yourself that the universe doesn't send signals. It simply behaves. Yet behavior without explanation can feel like intention. The anomaly's distance was estimated to be roughly 9,400 light-years away, deep enough into the Milky Way that dust clouds should have obscured the signal entirely. But the flicker cut through the dust as though it preferred to be seen. Astronomers joked about the universe turning on a flashlight, but privately, some admitted the truth. They had no model that explained why the light behaved as though choosing its own path. Further investigations showed that nearby cosmic rays bent strangely as they passed the region, curving in arcs inconsistent with the surrounding magnetic fields. It was as if an unseen geometry pressed against space, reshaping the trajectories of particles that should have moved in straight lines. The distortion wasn't strong, but it was precise, too consistent to dismiss as random fluctuations. You imagine yourself lying back as the stars ripple subtly, each wave carrying a question older than human memory. The uncertainty feels soothing instead of frightening. There's comfort in knowing that even the universe doesn't follow all of its own rules, that mystery is one of its natural languages. You feel small, but not insignificant, as though you've stepped into a story much larger than the explanations humans carry. The anomaly eventually earned a quiet nickname among the researchers, the tremor. Not because it shook violently, but because it unsettled assumptions. Every attempt to constrain it pushed against the limits of physics, as if the cosmos were gently tapping the edges of human understanding. No theory fit cleanly. No model predicted it. It existed like a contradiction, waiting for a new kind of science. You drift farther still, watching the pulse fade into the surrounding dark, the rhythm becoming softer, almost shy. The mystery doesn't resolve. It simply recedes, inviting more questions. And somewhere in that fading glow lies the sense that one unexplained phenomenon often leads to another, each stranger than the last, waiting deeper in the cosmic sea. And as the last ripple dissolves, something else begins to stir on the far horizon of the stars, quiet, distant, and carrying a different kind of impossibility, that pulls your attention forward without revealing why. You're drifting just beyond the edge of a star cluster, the kind that glimmers like dust caught in an invisible beam of light. Even from this imagined vantage, everything seems orderly. Stars orbiting their centers, gases following gravity's quiet pull. Yet somewhere inside this cluster, an object refuses to obey. Its motion doesn't align with the rules that govern everything else. It glides with a strange independence, as if space itself holds different instructions for it. Astronomers first noticed the anomaly while mapping stellar motions using Gaia's precise measurements. One star, faint, modest, easy to overlook, displayed a trajectory no equation could reproduce. It wasn't accelerating as gravity predicted, nor drifting randomly like debris perturbed by interactions. Instead, it seemed to change direction with a softness that suggested intentionality, even though that interpretation made no sense. Stars don't decide where to go. You hover above the fictional star, the cool backdrop of space brushing against your senses. Its movement seems gentle, like a leaf drifting across a pond without wind. You almost expect it to circle back, as though acknowledging your presence. The surrounding stars move predictably, bound in the choreography of celestial mechanics. But this one behaves more like a stray thought than an object made of fusion and fire. Researchers calculated its velocity, too low to escape its cluster, too high to remain bound, yet not matching the chaotic transitions between those states. Instead, the speed fluctuated with an eerie smoothness. It neither accelerated nor decelerated, it simply altered its value, as though space carried different densities in different pockets. No gravitational anomaly existed in that region, leaving scientists with a data set that seemed designed to resist interpretation. In the control rooms of observatories, scientists printed graphs showing the star's path. Instead of a clean curve or spiral, the track resembled brushstrokes, smooth transitions punctuated by abrupt but gentle shifts. A postdoc joked that the star was remembering something. No one laughed. They all stared at the data with the quiet discomfort that arises when reality refuses to match its own textbooks. You imagine reaching out and feeling the star's motion through your fingertips, sensing a subtle tug that doesn't belong to mass or momentum. The star feels like a drifting lantern, not bound to the cosmic tide. Its behavior creates a strange calm inside you, the same kind you feel when something unexpected happens gently, not violently. It unsettles and soothes you at the same time. Spectroscopic analysis didn't help. The star's composition was normal, a typical red subgiant with predictable internal processes. No hidden companion, no dark object tugging on it. Its light was steady, its temperature unremarkable. Everything about it screamed ordinary, everything except the way it moved. It was as though the star existed in two overlapping rulebooks, only one of which scientists could read. A graduate student suggested dust might be interfering with measurements, bending the starlight's apparent position. But dust moves slowly, and the star's changes occurred over weeks, not thousands of years. Interference patterns didn't match either. The observatories across Earth, from Chile to the Canary Islands to South Africa, confirmed the anomaly independently. Whatever was happening, it wasn't a glitch. You drift lower, watching the star pause, not literally, but perceptually, as though it hesitates, reconsidering its path. That's the illusion it creates, a cosmic pause, a breath held by something incapable of holding anything. The sensation blankets you in quiet curiosity. You don't feel fear. You feel the wonder that comes from encountering something honest and inscrutable. High-resolution images revealed tiny distortions around the star, like a faint shimmer in space-time. It resembled gravitational lensing, yet there was no mass to produce the effect. Something invisible might be nudging the star, but if so, it wasn't acting through gravity. It was acting through something science hasn't named yet, something that interacts with motion itself, not mass. In a small conference room, theorists gathered around chalkboards. They proposed exotic possibilities, modified inertia, hidden dimensions that alter trajectories, quantum-scale effects magnified across astronomical distances. Someone suggested the star might be entangled with another object elsewhere, but that idea fell apart under scrutiny. Cosmic entanglement doesn't steer stars like a puppeteer. You drift among the chalkboard ideas, their shapes swirling like the nebula around you. None feel right, but all feel possible. The universe often refuses the simplest explanations, preferring elegance that hides beneath layers of contradiction. You feel the scientists' frustration, but also their awe. They're confronting something that acts like a question rather than an answer. Gaia's updated measurements made the anomaly even stranger. The star's motion had shifted in a way that implied an unseen oscillation. Subtle, rhythmic, and unbelievably smooth. Not a vibration, but something like a soft breathing pattern woven into its trajectory. A motion that didn't belong to physics, yet repeated with quiet confidence. Engineers rechecked the spacecraft's calibration data. They reprocessed raw light curves, analyzed error margins, even simulated instrumental drift. But the anomaly remained stable across all methods. If anything, the star seemed to become more deliberate the more scientists tried to confine it to equations. It behaved as though acknowledging observation. You picture the star faintly pulsing as you hover nearby, a tiny ember in a dark ocean. It doesn't look extraordinary, yet its behavior reshapes the emptiness around it. You realize the mystery isn't dramatic, it's subtle. It doesn't roar, it whispers, and sometimes whispers reveal more about the universe than explosions. A team used machine learning models trained on millions of stellar motions. The anomaly confused them entirely. Some models interpreted it as two stars overlapping. Others thought it was a gravitational lens. One even classified it as an interstellar object accelerating under propulsion, though that idea was promptly dismissed. The machine wasn't wrong logically. It just didn't understand that stars shouldn't do that. In long meetings that stretched into early mornings, coffee brewing in the background, astrophysicists tried differentiating between data and interpretation. Was the star behaving strangely, or were humans interpreting a perfectly normal motion with inadequate tools? Yet no classical model reproduced the behavior. It stood alone, outside prediction. You drift farther from the star, now viewing its trajectory as a glowing line etched through the darkness. The line curves unpredictably, but elegantly, like handwriting in a language you've never learned. The beauty lies not in the chaos, but in the consistency of the inconsistency. The universe often reveals itself through contradictions. Researchers proposed a radical hypothesis that the star might be influenced by a topological defect, a relic from the early universe where space-time didn't fully smooth out. These defects are hypothetical, neither proven nor disproven. If real, they could distort motion subtly. But they're expected to be incredibly rare, and there was no reason one should sit quietly in a random star cluster. Observatories continued to track the star for years. The anomaly persisted unchanged, as if frozen in its odd behavior. No evolution, no escalation, just a steady defiance of Newton and Einstein. A cosmic shrug, a reminder that the universe doesn't owe humans consistency. You imagine floating away from the star, letting its mystery fade behind you. But as you move, the sensation doesn't leave. It lingers like a question that refuses closure. Some mysteries reveal themselves fully, others remain suspended, waiting for a future mind to reinterpret them. The scientists studying the anomaly eventually stopped trying to force it into old theories. Instead, they archived the data carefully, labeling it not as an error or misclassification, but as unresolved, a quiet word with enormous weight. A placeholder for a new physics not yet written. You drift into the wider darkness, sensing that mysteries often appear not as answers, but as gentle disruptions. The star's strange movement becomes a soft echo in your mind, nudging you deeper into the cosmic unknown. And in the distance, another unexplained phenomenon begins to emerge, one that doesn't just move strangely, but burns with an impossible kind of light you haven't yet imagined. You're drifting over a dark stretch of interstellar space where silence feels almost physical, like a soft fabric pressed gently against your senses. Ahead of you, a single point begins to shimmer, not like a star, not like a reflection, but like something remembering how to exist. It brightens with impossible speed. For a moment, it's as though the universe itself blinks, and then the light is gone, leaving only a faint afterimage suspended in the void. Astronomers first noticed these flashes when analyzing archival data from orbiting observatories. The burst lasted just milliseconds, too short for typical cosmic explosions. Yet during that fraction of time, it released more energy than many stars emit in years. It wasn't a supernova, nor the signature of a collapsing core. It was something else, something that appeared and vanished before instruments could fully react. You float closer, imagining the burst like a single exhale of creation. The surrounding darkness feels warm for an instant, as though the light left a memory behind. You sense the strangeness of it. Light isn't supposed to behave this way. It doesn't begin sharply and extinguish cleanly without some residual glow. But this burst ends with precision, like the closing of a cosmic shutter. Scientists measured the wavelength spread and found an anomaly. The peak arrived earlier than expected, as if some photons outran the others. But photons all move at the same speed, the universal constant that anchors physics itself. Yet the arrival times suggested an impossible truth. The light wasn't keeping the rules it's meant to define. The equations protested loudly. In mission control, a researcher rewound the data repeatedly, convinced the timestamping algorithm had glitched. She checked calibration markers, synchronized clocks across devices, even called a colleague in another country to rule out software drift. But the pattern stayed. Parts of the light arrived too early, as if drawn forward by a force nothing else responded to. You drift through the imagined region of the burst, the darkness trembling faintly. You feel as though something passed through this place, something too fast to witness, too gentle to disturb its surroundings. The emptiness feels charged, like a quiet room after a sudden shout. A lingering echo remains, not in sound but in sensation. Follow-up observations showed the burst repeated, but not predictably. It returned days later, then vanished for weeks, then resurfaced in a slightly different location less than a light minute away. No known object could jump that distance. The idea of a roaming source was proposed and discarded. The pattern made no sense unless something extremely small and unimaginably powerful moved through the region. At one observatory, an engineer questioned whether satellites crossing the telescope's field might cause false positives. But when cross-referenced with data from radio observatories, the burst appeared simultaneously in multiple wavelengths. Even gravitational wave detectors registered a faint tremor, a whisper below sensitivity thresholds, but statistically improbable to be noise. You imagine reaching out toward the region, feeling a faint hum against your palm. The hum isn't sound, it's the way the burst seems to vibrate in your memory. It behaves like lightning without clouds, like thunder without air, something that belongs to another set of physical rules entirely, intruding briefly into yours. The spectrum revealed a strange drop-off that didn't match any known emission process. Instead of cooling gradually, the energy curve fell sharply, as if the source simply stopped existing the moment it flashed. Supernovae, magnetars, and gamma-ray bursts all leave decay signatures. This phenomenon left none. It was abrupt, decisive, surgical. In theoretical physics groups, researchers debated exotic possibilities. Could it be a primordial object from the early universe, waking momentarily? A collapsing knot of space-time, or something interacting with a field humans haven't yet defined. The equations supporting these ideas were fragile, often collapsing under scrutiny. But the phenomenon itself didn't collapse. It persisted. You drift deeper into the scene, observing a faint distortion as though the darkness still holds the shape of a vanished flame. You sense the burst not as a violent event, but as a brief intersection, where two realities brushed against each other for an instant before retreating to places humans can't follow. The image fills you with quiet wonder. Scientists attempted triangulation using multiple telescopes worldwide. Doing so revealed something even stranger. The burst's origin appeared slightly different depending on the observatory. It had no fixed point in space. Instead, it behaved like a pattern projected from a dimension just misaligned with ours. Everyone agreed the idea was absurd, and yet the data persisted. Astronomers repeated analyses with more caution, reducing noise, adjusting baselines, ruling out every conventional explanation. The phenomenon remained stubbornly real. It didn't evolve or degrade. It simply continued to break rules in the same elegant way, as though demonstrating consistency within its own invisible framework. You float above, listening to the silence where the burst once lived. You notice how the faint glow in your imagination seems to shift slightly when you move your attention, like a memory trying to remain vivid. It's comforting in a strange way. The universe's mysteries don't always threaten. Sometimes they invite. The next time the burst appeared, radio antennas captured a pattern of interference resembling a spiral, but not a physical one. The data suggested a rotating structure with no mass, something interacting only with fields, not with matter. Yet nothing in physics allows rotation without particles or anchors. The idea was dismissed, then quietly revisited late at night by those who couldn't stop thinking about it. A young researcher created a simulation and found that the burst could be reproduced if space-time itself momentarily twisted. Not dramatically, just enough to compress and release energy like a spring snapping back into shape. But what could twist space-time so gently yet so powerfully? No known object or event matched the profile. You imagine that twist, a subtle bending of the emptiness around you, like the crease in a sheet that smooths itself as you watch. The image feels strangely peaceful, as though the universe were adjusting its posture. The burst becomes less of an explosion and more of a sigh, releasing tension from a place beyond human perception. Follow-up radio observations showed faint harmonics accompanying the burst, as though the event produced overtones similar to musical intervals. But space doesn't sing. It doesn't create harmonics unless something oscillates. The idea that space-time oscillated at those frequencies was both thrilling and terrifying. It implied a structure underlying reality that no current theory describes. In the lab, one scientist whispered that the burst felt like a poke from something trying to break through. The room fell silent, not because anyone believed in visitors, but because the comment touched a deeper unease, that the universe might contain events not meant to be understood yet. You float slowly away from the imaginary scene, sensing the unresolved nature of the burst tugging gently at your thoughts. The quiet feels heavier now, as though something enormous passed through, leaving ripples long after its disappearance. You don't fear it. Instead, you feel humbled. The scientists studying the phenomenon eventually divided into two groups. Those insisting it must be a natural process not yet categorized, and those who believed it signaled new physics. Both groups agreed on one thing: the burst demanded patience. Answers often require decades, even centuries of quiet observation. You hover at the edge of the darkness, watching for another flicker, but instead of light, what reaches you is a feeling, a sense that the universe sometimes reveals its contradictions in fleeting flashes, testing whether humans are paying attention. And just as the last echo fades from your mind, another unexplained anomaly begins to form elsewhere. Not in brightness this time, but in the strange way shadow moves in a place where shadow shouldn't exist. You're drifting across the surface of a quiet molecular cloud, where light from nearby stars scatters in soft blues and faint violets. Nothing here should cast a shadow. The dust is too thin, the illumination too diffuse, and the geometry too open for darkness to take shape. Yet as you glide through this imagined expanse, you notice it. A small, perfectly outlined patch of absence, moving slowly through the haze as if guided by something unseen. Astronomers first detected this void-like feature while examining infrared images from a deep survey telescope. At first, they dismissed it as calibration noise, a smudge from a detector pixel failing during exposure, but then the shadow shifted positions between frames, maintaining its sharp boundaries. It traveled as though carried by wind, except space has no wind, and nothing nearby could block light in such a precise contour. You drift closer to the shadow, watching the dust particles shimmer around its edges. Instead of blending softly into the surrounding cloud, the darkness has a clean perimeter, as if drawn with intention. Its movement is gentle, unhurried, giving you the uncanny impression of something pacing. The contrast makes the surrounding starlight look brighter, more fragile. Scientists checked the region's 3D density maps and found no object dense enough to obstruct starlight. Even a planet-sized mass would have produced gravitational influence, distorting nearby dust. But this shadow left no trace, no wobble, no lensing, no gravitational fingerprint. It moved like a silhouette with no physical body. In a research center, a pair of astronomers stared at sequential images pinned to a corkboard. The shadow's path curved slightly, following a pattern eerily reminiscent of a creature navigating terrain. Of course, they knew better. Space contains no such life, but the curve was too elegant to ignore. "It looks deliberate," one whispered, and the room fell quiet around her. You float through the darkness surrounding the shadow, feeling a faint chill in your imagination, as though your mind knows something is wrong before your reason catches up. The nebula should feel open and airy, yet this drifting darkness adds weight to the scene. It feels like an interruption, a skipped beat in the universe's rhythm. To probe further, astronomers examined the shadow's spectral signature. Surprisingly, the wavelengths passing through it were not merely dimmed, they were subtly shifted, as if stretched or compressed by a tiny ripple in space-time. This shift didn't match gravitational lensing or Doppler effects. It resembled an imprint left by something interacting with light without obstructing it. A physicist suggested it might be a void pocket, a region where the density of virtual particles fluctuates abnormally. But such fluctuations occur at quantum scales, not at distances large enough to be visible across light years. The idea was intriguing, yet impossible to justify. Still, the data seemed to whisper that something quantum-like had grown vast enough to cast a shadow. You drift closer until you sense the border of the darkness brushing against your awareness. It feels like stepping into a cool room from a warm one. Not dangerous, just unexpected. The shadow doesn't distort your imagined sight. It simply exists, calm and precise. You realize the discomfort isn't fear, but the quiet realization that a shadow without cause is more unsettling than any monster. Telescopes observing in multiple wavelengths found the same phenomenon. The shadow persisted in infrared, ultraviolet, and even microwave observations. No known material behaves this way. Dust becomes transparent at some wavelengths. Gas scatters or emits. But nothing stays consistently dark across such a broad spectrum without absorbing and re-emitting energy. The shadow emitted nothing. In mission archives, a researcher tracked the anomalies movement over months and found something even stranger. The shadow slowed and accelerated subtly, mimicking orbital motion without orbiting anything. It behaved like an object with inertia, but without mass. Something influencing motion without contributing gravity. You hover above, sensing how the anomaly shapes the surrounding light, bending it gently like a soft hand shaping water. The shadow doesn't pulse or flicker. It simply glides, leaving a wake of subtly altered starlight behind it. This wake is nearly invisible, detectable only through delicate analysis, but it reveals that the shadow interacts with the universe as though it belongs to a physics not yet taught. Scientists hypothesized the presence of a topological defect, a kind of wrinkle in space-time formed in the early universe. But such defects are expected to be incredibly rare, and even if present, they shouldn't produce mobile shadows. They'd remain stationary, anchored like scars. This one drifted as if free. A computational physicist ran simulations attempting to reproduce the behavior using altered metrics of space-time. Some attempts produced shadows, but none moved. Others moved, but they tore themselves apart mathematically. The anomaly's graceful motion refused to fit in any simulated universe, even one with experimental physics. You picture yourself following the shadow, feeling its path shift beneath you like a gentle current. You're not frightened, you're mesmerized. There's elegance in its wrongness, a kind of beauty in the idea that the universe contains shapes unaccounted for, like a language with missing letters that still forms coherent sentences. One night, during a discussion illuminated by the soft glow of computer monitors, a researcher wondered aloud whether the shadow might be a boundary, a thin membrane marking where an invisible field intersects with ordinary space. Others dismissed the notion until she plotted the field strength inferred from spectral distortions. The plot formed a symmetric shape too stable to ignore. Telescopes turned back to the region and found the shadow had changed slightly. Not in size or depth, but in orientation, as though rotating without spinning. Shadows on Earth rotate because their sources or surfaces move. But this shadow rotated in empty space, detached from any source. No one knew how to interpret that. You drift through the imagined dark and feel something shift, not physically, but in your understanding. The universe has always held mysteries, but some mysteries feel alive. Not in the biological sense, but in the sense that they adapt, respond, or persist with quiet intent. This shadow feels like one of them, a shape the universe allows but does not explain. Further examination revealed that the shadow's core temperature couldn't be measured. Not because it was too cold or too hot, but because it returned no thermal data at all, not even noise. It was as if the region ignored the rules of thermodynamics. It didn't absorb energy, radiate it, or equalize with its surroundings. It simply remained blank. Teams proposed the radical idea that the shadow might be a spatial boundary, between normal space-time and a region of altered dimensionality. If true, the shadow wasn't the thing, it was the edge of the thing, the universe, showing only its outline. You drift back slowly, watching the darkness glide onward with quiet purpose. It's not threatening, it's indifferent, and there's something strangely comforting in knowing the cosmos contains enigmas so gentle. You let the shadow drift past you in your imagination, dissolving softly into the larger night. As it fades, you sense that mysteries aren't isolated. One leads to another. Shadows follow bursts, and bursts follow tremors. Somewhere deeper in the universe, a phenomenon waits that doesn't hide in darkness or light, but in the strange behavior of time itself. A faint shimmer settles across your imagination, almost like static from a distant universe brushing against the edge of your awareness. In that shimmer lives a story scientists still can't tell without pausing, because it begins with a signal that simply should not have arrived when it did. The whole mystery started at a quiet neutrino observatory buried deep under Antarctic ice. Rows of photodetectors sat in perfect darkness, waiting for ghostly particles to pass through. Most neutrinos ignore detectors entirely, but every so often one leaves behind a pale flash of blue light. In one strange event, the light appeared far too soon. Somewhere in that icy darkness, a burst of illumination triggered a timestamp that contradicted physics by arriving slightly ahead of the photon-based timing signals. It was as if the particle had taken a shortcut through reality, not faster than light exactly, but earlier than it should have been allowed to exist in the detector. A scientist reviewing the logs rubbed his eyes repeatedly, assuming the timestamp had glitched. But backup systems confirmed the anomaly. 3 independent clocks, synchronized by atomic oscillations, agreed. The particle's arrival time didn't make sense. Inside the underground lab, the silence grew heavier. Researchers rechecked GPS synchronization, cable delays, thermal drift, and signal propagation. Every system behaved normally. The only abnormality was the event itself, appearing like a quiet contradiction glowing faintly against cold, unclear ice. Imagining the scene, you might sense the pressure of the earth overhead, muted vibrations of distant storms passing through rock. In that stillness, the anomalous signal feels almost alive, like a soft knock on a door humans didn't expect to hear from the universe. When the data was compared with measurements from gamma-ray observatories, an even stranger detail emerged. The neutrino had originated from a distant cosmic explosion. Light from the same event reached Earth later than predicted, by just enough to raise uncomfortable questions. It wasn't a large discrepancy, but it was real. Some physicists wondered whether the neutrino had traveled along a slightly curved path through warped space-time, arriving early not by breaking speed limits, but by taking a subtly shorter road. Yet simulations of the region's gravitational landscape showed nothing unusual, no massive objects, no distortions. Others proposed that the particle might have tunneled through space-time in a quantum sense, skipping a portion of its journey the way electrons sometimes bypass barriers. But such tunneling shouldn't work across light years. It shouldn't leave a detectable signature at all. Back in the Antarctic darkness, engineers examined the detector modules one by one. They calibrated voltage lines, replaced connectors, and ran cold tests. All systems behaved impeccably. No faulty wiring, no jitter, no corrupted memory. The detector had done exactly what it was designed to do: capture impossible evidence. Images of the event spread through research teams, showing a faint cascade of Cherenkov light blooming like a small ghost trapped inside the ice. It didn't look remarkable. yet the implications twisted physics into knots. Something had allowed the particle to cheat the expected sequence of cosmic events. As you picture the faint glow, you may sense an odd calmness in the scene, as if the universe isn't concerned that its rules appear inconsistent. Humans crave order. The cosmos seems content with ambiguity. To compare possibilities, researchers pulled ancient data sets from the observatory's archives. Buried inside the noise, they found two earlier events with eerily similar timing irregularities. They were dismissed at the time as instrument noise, but now they formed a pattern. Once per decade, a particle arrived too early. One physicist suggested an exotic explanation, that neutrinos might oscillate into a new, unknown state that interacts differently with space-time. This sterile form could slip through geometric folds predicted in certain theories but never proven. If true, the anomaly wasn't a glitch, it was a hint. Far from the ice, in a cramped office filled with scribbled equations, a researcher plotted the timeline offsets and produced a curve so smooth and elegant, it felt like a cosmic whisper. Something out there seemed to obey a rule humans hadn't discovered yet. You might imagine sitting at her desk, hearing the soft hum of the heater, the ticking of a pencil against paper. These human details blend with the cosmic puzzle, reminding you that breakthroughs often begin in ordinary rooms, with people blinking in disbelief at numbers that refuse to behave. The anomaly resonated across the scientific community, not because it proved faster than light travel, but because it suggested a loophole, a place where classical ordering of events becomes flexible. When cause and effect bend even slightly, physicists feel the floor shift beneath their feet. Observatories worldwide pointed sensors toward the region of sky where the neutrino had originated. Weeks later, they captured a faint afterglow, a gamma-ray echo far weaker than expected. The timeline was wrong again. Something about the entire event sequence felt scrambled. Simulations combining both data sets revealed an unexpected possibility. The neutrino might not have traveled early at all. Instead, the surrounding space-time could have stretched differently during the explosion, altering the expected arrival sequences. But no known mechanism explains such selective stretching. You may sense the puzzle tightening, like fabric pulled gently from multiple directions, forming a pattern without revealing its origin. That's what the scientists felt too, an elegant inconsistency. In long conference calls lit by the pale glow of laptop screens, theories clashed. Some invoked quantum gravity effects. Others blamed dark energy fluctuations. A few quietly wondered whether time itself behaves differently, near cataclysmic events than models predict. The idea felt sacrilegious, yet irresistible. What if time isn't a uniform river, but a landscape with ridges, pools, shortcuts, and unexpected hollows? As researchers argued, the early neutrino remained silent, just one more entry in a long list of cosmic riddles. But the memory of that faint pulse beneath the ice lingered in every conversation. Some theories proposed that the particle had interacted with an unknown field, a kind of temporal lens that nudged its path. But such a field hasn't been detected anywhere else. If it exists, it hides exceptionally well. And yet, the data persists, like a gentle tap on the shoulder from the universe. Not forceful, not urgent. Just noticeable enough to say, something is different here. The more scientists examined the anomaly, the more they noticed subtle irregularities in similar events around the world. None were definitive, but each one nudged their intuition toward the same quiet question: are these particles revealing a crack in the sequence of time as we understand it? Across the Antarctic ice sheet, the wind howled as if carrying secrets through frozen emptiness. Beneath the surface, the observatory waited, patient and silent, hoping for another impossible flash. You might picture that quiet chamber, knowing the next unexpected signal could arrive at any moment. Unannounced, uninvited, and completely unexplainable. And somewhere in that uncertainty, a deeper mystery begins to take shape. One that does not travel early or late, but moves sideways through understanding itself. A soft haze settles across your thoughts, the kind that comes when the night feels too still, too observant. In that quiet, a story begins, one about a cosmic signal that arrived perfectly, cleanly, unmistakably, and then disappeared as if erasing its own footsteps. Far across the universe, a distant star system unleashed a burst of radio waves, sharp, structured, and unlike common cosmic noise. The pulse had the mathematical crispness of something intentional, though no one dared to say that out loud. When the data first streamed into the Australian Square Kilometre Array Pathfinder, technicians saw a pattern that made them lean closer to their monitors. A rising-falling oscillation, too regular to dismiss. It lasted only seconds, but those seconds felt like an entire doorway being nudged open. Inside the control room, fluorescent lights hummed as researchers replayed the waveform. Each replay deepened the mystery. The pattern contained a repeating interval that didn't match pulsars, quasars, magnetars, or the usual suspects of cosmic rhythm. You might imagine yourself standing behind those scientists, hearing the faint electronic buzzing, smelling warm circuitry, feeling the tension rising in the room the way static builds before a storm. Something about the signal pressed against intuition. The pulse seemed to originate 1/900 light-years away, a region containing no known energetic objects capable of such a clean pattern. Background sources were ruled out. Satellites were ruled out. Terrestrial interference was ruled out. The team had triple-checked before sounding the alert. Other observatories turned their dishes toward the coordinates. For a fleeting moment, they confirmed it, a faint echo of the same structured pulse. And then, mid-measurement, everything went silent. No fading, no distortion, just abrupt, perfect absence. One instrument caught the tail end of the signal ending, half a second earlier than the others, as if the broadcast had been cut off unevenly. That tiny discrepancy ignited the first wave of confusion. Signals traveling through normal space should extinguish uniformly, not stagger. In response, scientists re-examined the initial burst. The waveform wasn't just clean. It seemed deliberately confined to a narrow frequency range, like something choosing its lane with unnatural discipline. You float in the imagined darkness of the cosmos surrounding that star system, sensing nothing around you except a thin thread of energy stretching from a distant point to Earth. A thread pulled taut, then suddenly severed. Back on Earth, anxious researchers began searching for artifacts in the data pipeline. They tore apart their code, looking for misaligned buffers, corrupted bits, jitter from thermal drift. Nothing. The anomaly wasn't inside the computers. To uncover more clues, they synchronized logs from every observatory involved. And that's when a new oddity emerged. The signal's arrival time across continents appeared slightly out of sequence, not enough to violate physics, but enough to look wrong. Global networks operate with nanosecond precision. These mismatches felt like seeing shadows bending opposite their light source. The numbers didn't align with any known astrophysical behavior. Some theorists proposed that the signal had passed through a region of turbulent space-time, where gravitational ripples distorted its timing. But gravitational waves would have left detectable fingerprints. None were found. Others suggested plasma lensing, interstellar clouds refracting radio waves in complex ways. Yet plasma refraction usually distorts or scatters a signal, not sharpens it. You imagine looking at the night sky from your window, the stars pinned like delicate sparks. Somewhere among them sits a silence shaped exactly like the vanished signal, a silence too precise to be accidental. Meanwhile, engineers tried reconstructing the waveform, breaking it into segments, analyzing bit patterns. In those fragments, they found intervals that felt almost purposeful, ratios stable to many decimal places, like a musical chord held in cosmic tension. But before anyone could dive deeper, the archived data showed another impossibility. The recorded signal began shifting, not changing but misaligning, as if segments were drifting milliseconds from their original timestamps. Archival data does not move. The team suspected a data corruption event, yet checksum verifications proved the files were intact. Something about the structure of the signal seemed to interfere with the storage itself, not breaking it, but nudging its alignment sideways. As days passed, the scientific community proposed increasingly exotic models. Some invoked topological defects, cosmic strings vibrating across space-time. Others suggested that the source might be hidden behind a gravitational lens that flickered unpredictably, causing the observed disappearance. But a quiet minority whispered a more unsettling theory. The signal didn't vanish. It completed whatever it intended to do. Picture a ripple on a glassy lake. It travels outward, touches the shoreline, and dissolves. The mystery isn't its disappearance. It's why it formed such a perfect shape in the first place. Scientists scheduled repeated observations of the coordinates. Night after night, dishes waited, static, silence. Not even a faint whisper reminiscent of the original pattern. The universe kept the remaining answers tucked behind a curtain. During a late-night meeting lit by monitors and half-empty coffee cups, an astrophysicist suggested something no one wanted to discuss. What if the signal exists only at the moment of detection? In other words, not a broadcast from afar, but a phenomenon emerging when conditions briefly synchronize. You feel the weight of that thought, the idea that some cosmic events exist solely at the intersection of observer and universe, like dew forming only when air and temperature agree. In this interpretation, the signal wasn't a message. It was a coincidence of physics so rare it imitated intention. Even now, archived copies of the signal behave strangely. In some analyses, its harmonics appear enhanced. In others, they fade. As if the event resists being fully pinned down, the way a dream loses clarity each time you try to recall it, the mystery continues to breathe quietly through research papers, conference halls, and late-night discussions in labs worldwide. It isn't famous, not publicly, but among those who study inexplicable cosmic events, it remains a soft, persistent riddle. What scientists saw was undeniable. What they still can't explain is why the universe allowed the signal to appear once, and only once, before folding itself back into silence. There's a quiet weight in the air as you settle deeper into your pillow, a feeling like the night is holding its breath for a story too improbable to ignore. Far beyond the Milky Way's spiral arms, astronomers once stumbled upon something that seemed to stretch not just across space, but across the limits of what physics allows. And from the moment it appeared on their screens, it pressed the same question into every mind watching. How can something so enormous even exist? It began with a routine sky survey, one of those patient, methodical scans meant to catalogue galaxies like notes in a cosmic ledger. Yet in the data, a faint alignment emerged. At first, it seemed like nothing. A handful of bright points lined up loosely across billions of light years. But as more data accumulated, the alignment extended, swelling into a thread-like structure so vast that researchers assumed they were looking at an error. Imagine yourself in that dim room with them, the overhead lights humming, the glow of monitors reflecting in tired eyes. Someone zooms out on the map, then zooms out again and again. The line doesn't break. It continues like a stitched scar across the universe, an unbroken chain of quasars spanning nearly 4 billion light-years. The problem isn't that quasars can line up, it's that nothing on that scale should line up. According to standard cosmology, the universe should look homogeneous at sufficiently large scales. Beyond a few 100 million light-years, patterns are supposed to dissolve into statistical randomness. But this structure, later called the Giant Quasar Group, refused to dissolve. Scientists triple-checked the coordinates. They reprocessed raw telescope feeds. They verified redshifts independently. The structure was real, no glitch, no cosmic coincidence. Something enormous was threading quasars into a shape the universe's rules tried to forbid. You picture yourself floating near the edge of that impossible formation, suspended in cold silence. Each quasar is a roaring engine, brighter than entire galaxies. Yet from where you drift, they look like quiet embers arranged deliberately across a darkened canvas. There's a tension in the alignment, like an invisible hand brushed through the cosmos and left a trace. Back on Earth, theorists scrambled. One proposed that the structure might be a remnant of quantum fluctuations stretched during inflation. Another argued it could be a projection artifact caused by large-scale gravitational lensing. Both theories fell apart under scrutiny. To probe deeper, researchers plotted the position of each quasar in three-dimensional space. When rendered, the structure twisted slightly, forming a subtle arc instead of a straight line, almost serpentine. This curvature made the mystery worse. Random clustering doesn't curve so deliberately. Engineers revisited the survey instruments, dissecting every component. Fiber links, CCD sensors, calibration lasers, everything was checked. The error budget remained too small to explain a structure this large. One scientist joked, half serious, "If this is an artifact, it's the most consistent mistake ever made." As months passed, the structure forced cosmologists to reconsider assumptions about cosmic isotropy. If the universe wasn't as uniform as expected, what else might be hiding in these unfathomable scales? The more they explored, the more the laws seemed to wobble around the edges. You sense that wobble, a gentle unsteadiness, like the moment before you fall asleep when shapes blur and meanings loosen. In the vastness of the cosmos, maybe not everything follows the tidy patterns we expect. Maybe some things grow wild. But then came the stranger part. Adjacent sky surveys found another large-scale structure, this time a gamma-ray burst ring measuring 5 billion light-years across. Two impossibilities appearing within a cosmic blink of each other. Statistically, it was like rolling a trillion-sided die and hitting the same impossible number twice. Researchers convened emergency workshops. PowerPoints flickered across conference halls. Data poured across laptops. And the more they tried to overlay the structures, the more unsettling it became. Their orientations differed, yet both were too large, too organized, too deliberate. You imagine leaning over the railing of existence, looking down at patterns engraved in the universe that no one fully understands. It feels like standing in a forest and realizing the trees around you form a shape only visible from miles above. Some scientists wondered whether these structures marked the gravitational scaffolding of the early universe, a blueprint etched before matter condensed. Others feared something simpler. Maybe our models are only approximations of a reality far stranger and more tangled than we admit. Human experiments continued, new telescopes mapping deeper, wider, faster. Data pipelines grew more sophisticated. researchers implemented machine learning classifiers to detect similar structures in older surveys. And that's when something unexpected surfaced. Faint suggestions of patterns in regions long considered empty. The implication was chilling. Maybe these structures weren't anomalies. Maybe they were common, we just never looked closely enough to recognize them. Yet each time someone proposed a unifying explanation, contradictions appeared. The structures violated the cosmological principle. They resisted inflationary predictions. They bypassed accepted clustering mechanics. They didn't fit neatly into dark matter models. Every theory collapsed under weight of its own complexity. You feel the tension of unsolved knowledge, the way your heartbeat quiets when you meet a mystery too big to wrestle with. Sometimes the universe feels like a riddle told by someone who enjoys withholding the punchline. Still, the giant quasar alignment remains unmoved, spanning epochs, staring silently across space-time. No signs of decay, no gravitational distortions expected at that size, just a patient, impossible presence. Some researchers privately admit that the structure feels intentional, not in a conscious sense, but in its coherence, like a cosmic tune repeating across impossible distances. They know the universe isn't supposed to write melodies this large. When you let your mind drift across that scale, you feel yourself shrinking, not in fear, but in awe. The mystery becomes a kind of lullaby, a rhythm older than galaxies, humming softly through the void. And as scientists continue their search, another whisper rises between the unanswered questions. One few dare say aloud, if this is only one structure we happen to find, how many others are still waiting in the dark? Some mysteries arrive quietly, slipping into experiments that were never meant to find anything extraordinary. You can imagine the fluorescent hum of a laboratory late at night, the stillness of a room where only a few exhausted physicists remain, half running on caffeine, half running on stubborn curiosity. Somewhere in that hush, a blip of data appeared, one so small it should have been irrelevant, yet so out of place it made the entire team lean closer. What they saw came from a beam experiment measuring muons, fleeting, unstable particles that normally obey predictable rules. But that night, the muons acted as if they were listening to a different conductor, spinning slightly faster than theory allowed. Not enough to panic anyone, but enough to whisper something doesn't add up. You feel the tension of that moment, like staring at a clock whose second hand jumps strangely, though you can't explain why. Most physicists dismissed it as noise, a calibration error, a magnetic fluctuation, or the rounding quirks of old equipment. Yet the anomaly persisted, appearing again and again, tiny but defiant. In particle physics, consistency is everything. If something unusual happens once, it's ignored. Twice it's interesting, a dozen times, that becomes a problem. The muon anomaly refused to disappear, no matter how often detectors were replaced, recalibrated, or rebuilt from scratch. As you lie there in the quiet of your room, you can visualize the experiment. Rings of superconducting magnets forming a perfect circle, a narrow beam of particles racing around like fireflies trapped in a cosmic racetrack. Each muon spins as it moves, twirling in the magnetic field. Theory predicts exactly how fast that spin should precess, but in reality, the spin was off, just slightly, just enough to hint at forces we haven't named yet. The discrepancy was small, yet profound, roughly 4 parts per million. But in physics, a whisper can be an earthquake. Scientists dug deeper. They ran Monte Carlo simulations, swept through piles of equations, inspected magnetic field maps millimeter by millimeter, and every time they expected to find a mundane explanation, the data pushed back with the same stubborn signature. Imagine standing over the experiment, the air cold and dry, the floor vibrating faintly from distant equipment. You watch the moon zip around, each one flickering into existence for microseconds before decaying into electrons. Those electrons carry the final trace of the moon's dance, and the trace says something else is at play. The baffling part was that no known particle or field could explain the deviation. The standard model, our most trusted map of reality, had no room for this behavior. It was as if a page of physics had been torn out, leaving behind only the faint outline of what once belonged there. And just when the puzzle seemed too small to matter, another layer appeared. A different anomaly, this time from proton radius measurements, revealed a similar inconsistency. Two unrelated experiments whispering the same unsettling message, researchers refused to give up. They redesigned entire apparatuses. They recalculated constants. They swapped lasers, detectors, magnets. They even questioned the fundamental values they had been using for years. But no matter how they approached it, the muon anomaly held its ground. There's a strange comfort in this, a reminder that the universe does not always give up its truths easily. You feel that comfort now, settling under the weight of your blanket, letting the unknown breathe softly around you like a tide. During a major run at Fermilab, the anomaly sharpened. A fresh measurement confirmed the result with even higher precision. The deviation wasn't an illusion. Something truly was tugging at the moons, nudging their spin like a hidden breeze brushing across an invisible field. Theorists proposed explanations that bordered on science fiction. Dark photons, supersymmetric partners, exotic fields left over from the early universe. Each idea glittered with potential, yet none survived the harsh interrogation of the numbers. And so a quiet confession began circulating in academic hallways. We don't know what's doing this. You picture a chalkboard cluttered with equations, crossed-out guesses, and hopeful theories circled in red. The air smells of dust and coffee. Late-night debates stretch into early morning silences. Someone writes "new physics" in the corner and leaves a question mark dangling like an unanswered prayer. Meanwhile, other scientists reviewed historical data from particle accelerators decades old. To their surprise, hints of the same anomaly had been buried there unnoticed, waiting to be recognized. The past had been whispering the same secret all along. As you listen to this unfolding mystery, you may notice your breathing slowing, syncing with the rhythm of the story. The unknown has a way of softening the edges of thought, inviting you to rest in curiosity rather than certainty. Yet one detail remains especially haunting. The anomaly seems stable over time. It does not fluctuate or fade. It stands like an immovable pebble lodged inside our best theories, a persistent reminder that the map of reality must one day be redrawn. Researchers continue their work with a kind of reverent frustration. Every new measurement deepens the strange curve of the puzzle. And every improvement in precision further isolates the anomaly as something real, something waiting. You can almost feel that waiting, like the hum of a machine cooling in a silent room, or the stillness of a star just before it collapses into brilliance. Some mysteries demand patience, and this one seems carved out of that patience. But perhaps the most intriguing thought is the one scientists rarely speak aloud. What if the muon anomaly isn't an error in the theory? What if it's a doorway? Because sometimes the smallest deviation becomes the first crack through which a new universe begins to reveal itself. And somewhere beyond those cracks, another unexplained phenomenon waits with equal persistence. Another whisper in the vast machinery of reality, asking to be heard. There are stars that burn predictably, living out their lives in steady, rhythmic pulses of fusion. And then there is the one astronomers found that seemed to behave like a nervous heartbeat, bright one moment, dimmed the next. as though some cosmic hand were lowering a curtain across its light. No ordinary star flickers like that, not naturally. You might picture yourself standing beneath a clear night sky, watching a single point of light blink in a way no star should. That's how the discovery felt, a quiet signal against a backdrop of certainty, asking to be noticed. What scientists found was a star whose brightness dropped by nearly 20% at irregular intervals, far too dramatic for any known cause. Dust clouds could dim starlight, yes, but never by that much. Planets could pass in front of a star, but their shadows follow predictable patterns. This star refused every explanation. The mystery deepened when long-term observations revealed that the star wasn't just flickering. It was slowly fading, year after year, as if dissolving into the backdrop of space. No known stellar cycle causes that kind of decline. Teams across the world scrambled to collect more data. Telescopes from Hawaii to Chile pivoted toward this object, capturing every dip in brightness with increasing urgency. Yet every dip looked different from the last, a chaotic fingerprint with no clear rhythm to decode. As you lie there, you may imagine astronomers huddled around computer screens late at night, sipping lukewarm coffee while graphs update in real time. Each sudden drop in luminosity would have filled the room with a small shock, followed by silence, the troubling kind, heavy with unspoken questions. Some proposed that a giant field of comets might be swarming the star, occasionally blotting out its light. Others suggested vast, uneven dust rings, but both ideas collapsed under scrutiny. The patterns didn't match. The dips were too sharp, too irregular, too deep. You can sense their frustration as they turn to more exotic ideas. The star might be shredding a planet, scattering debris into orbit. Or perhaps a colossal disk of material was warping under gravitational stress. But again, the models fell apart. Then came the hypothesis most people whispered rather than spoke aloud: megastructures. The kind you'd expect from a civilization far older and more advanced than ours. Not because anyone believed it, but because nothing else fit neatly into the data. You can almost feel the discomfort of that possibility, like a breath caught halfway in your chest. Scientists dislike jumping to extraordinary conclusions, yet extraordinary behavior demands a long, honest look. Observatories pointed their radio antennas toward the star, searching for artificial signals, anything that might hint at an engineered structure dimming its light. The result was absolute silence. Not even cosmic static of interest, just the background hum of a universe indifferent to our curiosity. And still, the dimming continued. Imagine yourself in that lab again, listening to the soft whir of cooling systems as astronomers monitor data pouring in. The star dips again, not as deeply as before, but enough to reignite every debate. Someone scribbles on a whiteboard, crossing out previous theories, adding new diagrams that spiral into uncertainty. The most unsettling part wasn't the lack of answers. It was the abundance of almost answers. Every explanation came close to fitting, but never fully. Like trying to complete a puzzle where several pieces are missing and the picture on the box keeps changing. The star seemed to behave as though ruled by laws that don't apply anywhere else. Or perhaps the laws do apply. We just haven't discovered them yet. You might think of the star as a storyteller speaking in a forgotten dialect. Its shifts in brightness forming a language modern astrophysics has yet to learn. The frustration, the awe, the humility, it all blends into the long hours scientists spent watching that stubborn speck of light. Researchers reanalyzed old sky surveys and discovered that the star's fading had been happening for over a century, unnoticed. What seemed like a new anomaly had been quietly unfolding across generations. A cosmic drama so slow that only patient, persistent eyes could ever have seen it. The star's strange behavior remains unsolved, though some patterns have emerged, enough to rule out the more sensational ideas, but not enough to reveal a satisfying truth. Even now, teams continue monitoring it, hoping that one dip, one resurgence of brightness, one curve in the data might unlock the hidden mechanism behind it all. You can feel the quiet persistence in that search, as steady as your breathing. Mysteries like this one rarely shout their answers. They whisper, they flicker. They test our willingness to stay curious. And somewhere in the tension between fading and brightening, a deeper question lingers. Is the star changing? Or are we simply learning to see? The truth remains beyond reach, for now. But the star continues its silent performance, a reminder that even the familiar glow of starlight carries secrets. And just when astronomers thought they had catalogued its every strange behavior, another phenomenon appeared, not in brightness, but in the spectrum of the light itself, hinting at something even stranger waiting beneath the surface. A mystery inside a mystery, unfolding one wavelength at a time. There are moments in science when data behaves too neatly, too rhythmically, too deliberately. Patterns like that tend to raise eyebrows and heart rates. When astronomers first noticed a radio pulse repeating every 1.337 seconds with near-perfect consistency, they froze. Nothing in the sky should keep time that well. Picture yourself in a dim control room, the glow of monitors painting the air blue as a precise spike appears on the graph, then another and another. Like a cosmic metronome tapping on the door of human understanding. At the time, no known natural object could produce such a crisp, ticked repeating signal. Stars flicker, yes, but not with industrial precision. Black holes devour light, but they don't blink. Gas clouds swirl, but they don't keep time. This pulse did, all night long. The team labeled it LGM-1 as a joke, Little Green Men. Not because they truly believed that, but because humor is sometimes the only way to cope with data that refuses to behave. Still, they tested for interference. Was the signal coming from a nearby transmitter, a plane, a satellite? Every possibility was crossed out with methodical frustration. The pulse persisted. Same rhythm, same strength, same eerie regularity. Imagine leaning closer to a screen, holding your breath. Not because you expect aliens, but because this kind of order in the universe feels intentional. When more telescopes pointed at the source, the pattern remained. A bright flash of radio waves, followed by darkness, repeating as faithfully as a heartbeat. The intervals were so exact that atomic clocks could have used them for calibration. But science asks for patience, not fantasies. As data accumulated, the astronomers widened their search, sweeping across adjacent regions of the sky. And then something remarkable happened. They found another pulse, distant, faint, and repeating in its own rhythm. Two cosmic metronomes, not one. Now the mystery deepened. If a single pulse was strange, two made coincidence seem unlikely. Yet the signals had different timings, different intensities, different spectral shapes. Whatever was happening, it wasn't planned. It was natural. Somehow. The turning point came when the team realized that the pulses weren't coming from objects orbiting the sun. They traced far beyond the Milky Way. Nothing human-made could reach those distances, and nothing human-made could be that consistent. You might imagine the moment the realization clicked into place. A star collapsed into a neutron star, spinning so fast that beams of radiation swept across space like the light of a cosmic lighthouse. Each rotation produced a pulse. But how could something so chaotic an exploded star crushed into a sphere the size of a city, rotate with such mechanical precision. Even now, neutron stars defy intuition. A teaspoon of their matter weighs billions of tons. Their magnetic fields could erase a hard drive from the distance of the moon. And yet, in their monstrous violence, they rotate with ballet-like order. Astronomers named them pulsars, but the name solved nothing. It only described what was observed, not why it worked so flawlessly. Imagine lying quietly as the thought sinks in. The universe contains clocks older than civilizations, older than mountains, older than Earth itself. Clocks that never burn out, never slow down, never forget their cadence unless pushed by forces beyond comprehension. The discovery reshaped astrophysics overnight. It confirmed that nature could mimic intention, producing patterns so exact that even the most skeptical minds hesitated. More pulsars were found, each with its own rhythm, each a reminder that regularity does not imply intelligence, and mystery does not always require agency, but the initial shock never faded. Yet something about the first discovery remains strangely human. The fact that scientists scribbled LGM in their notes reveals something intimate. Even the most disciplined researchers are not immune to wonder. It's comforting, in a way, to know that our first instinct wasn't fear or dismissal. It was curiosity, dressed as humor. A small acknowledgement that the universe still has the capacity to surprise us. You can picture the original radio dish, still standing, still listening, surrounded by quiet fields and wind. If you were there, leaning against its metal frame, you might hear the faint echo of those pulses, not as sounds, but as a reminder of how easily our minds leap toward meaning. Pulsars solved the mystery of the original signal, but they also opened a new question. How many other impossible patterns in the universe are simply natural laws we've not discovered yet? It's that thought, the possibility that mystery is not an obstacle but an invitation, that guided astronomers as they moved on to new anomalies, new irregularities, new whispers from the cosmos. And just when they thought they had mapped the predictable world of pulsars, another signal appeared, one that refused every pattern, every expectation, every previous lesson. A signal that behaved as if the rules had shifted again. There are moments when the universe seems to hesitate, as if choosing whether to reveal something or keep it hidden. What astronomers detected next didn't behave like anything they had catalogued before. Not periodic, not chaotic, not random, but something in between. Like a message written by a hand that didn't care whether it was understood. Imagine yourself in a quiet room, lights low, as a grainy graph flickers on a scientist's laptop. Instead of clean spikes or scattered noise, the line trembles in delicate crescents, rising and falling as though following the breath of a sleeping giant. The signal didn't repeat, yet it wasn't disorderly either. Every burst looked eerily similar to the previous one, but spaced apart with no rhythm science could measure. The intervals were too irregular to be mechanical, too consistent to be chance. At first, the researchers suspected interference, a truck engine, a faulty microwave, a nearby phone tower. Any of these could contaminate the data, but interference tends to smear itself across frequencies. This anomaly stayed razor-thin, clean, almost proud of its clarity. Picture a cluster of astronomers crowding around a monitor, shoulders tense, coffee forgotten, as the dish outside turns through the cold air to confirm whether the anomaly repeats. And then, minutes later, another burst, similar shape, different timing, mocking their anticipation. The team cross-checked multiple telescopes across continents: Australia, Chile, the Canary Islands. Each one captured the same skewed crescents, arriving at unpredictable intervals. Whatever it was, it spanned half the globe in visibility, and it wasn't local. Some suggested a new kind of pulsar glitching erratically, but pulsars do not glitch in shape so uniform. Others proposed collapsing magnetars shedding layers of energy, but magnetars howl in frequencies far more violent than this whisper. Imagine the sensation of leaning closer to a dataset, the world fading around you, because the lines on the screen look too intentional to ignore. Even if your rational mind knows nature is indifferent, your instincts can't help but feel watched. The astronomers fed the bursts into Fourier transforms, into neural networks, into old algorithms once used for earthquake predictions. Every tool returned the same conclusion. This signal fit no known category. It grew stranger. Bursts sometimes arrived in clusters, 3 within a second, then silence stretching for hours, then a single burst, wider than the others, with a shape uncannily similar to the first detection weeks earlier. Patterns without patterns, order inside disorder, a structure refusing interpretation. Eventually, human curiosity turned into collaboration. Researchers who rarely agreed on anything began sharing code, comparing raw files, even flying across continents to sit beside one another in front of the same blinking graphs. Picture them adjusting antennas by hand, tightening bolts under starlight, brushing frost off control panels while the dish shifts to follow a faint, elusive whisper slipping through cosmic background haze. Spectral analysis revealed something new. Each burst contained substructures, small ripples nested inside the main curve, like echoes bouncing within a canyon of magnetic fields. But the spacing of these ripples changed from burst to burst, obeying no law anyone recognized. Theories multiplied. A supernova remnant interacting with a filament of plasma. A neutron star tangled in unfamiliar magnetic knots. A black hole's accretion jet flickering through turbulent dust. But no single model could produce both the consistency of shape and the inconsistency of timing. Even more unsettling, the bursts seemed to wander across the sky by microscopic degrees, not enough to indicate motion, just enough to complicate every explanation, as though the signal were smeared through space by something we do not yet understand. And then came the moment no one expected. A researcher recalibrating an old detector discovered that when the bursts were plotted in reverse, time flipped backward, their internal ripples aligned more neatly than any forward time analysis could achieve. It was as if the signal made more sense when read from the end to the beginning. No natural phenomenon behaves that way, or at least none we've studied long enough to recognize. For a while, the discovery remained quiet, not hidden exactly, but spoken about in whispers at conferences, scribbled into notebooks, or passed along in late-night emails accompanied by phrases like, "This can't be right," or "Look at this again when you're awake." Imagine yourself alone in a room, listening to the thought settle. Some mysteries refuse to remain consistent because consistency itself is part of the illusion. They lure us closer by being almost familiar, then slip away the moment we think we've understood them. Scientifically, there was still no breakthrough. Philosophically, there was something new lingering in the air, an acceptance that the universe might be structured in layers of intelligibility, some of which humans were never meant to peel back quickly. And as the team prepared to aim more powerful equipment at the anomaly, the bursts suddenly paused. Not faded, not weakened, paused, as if the phenomenon sensed attention and chose silence. But silence in astronomy is never empty. It's an inhale before revelation. When the bursts stopped, the first reaction wasn't relief, it was dread. A constant anomaly can be studied. A vanishing one feels almost personal, as though the universe had closed a door just as humanity reached for the handle. For several nights, the telescopes swept the same coordinates, listening to a cosmic quiet so deep it felt staged. At one observatory, a scientist sat alone in the dim glow of the control room, the hum of the servers masking the heaviness in her chest. She replayed the old bursts on a loop, adjusting filters, changing color maps, searching for hidden threads she might have overlooked before the silence fell. Silence in space isn't the absence of sound, it is the absence of answers. And you, lying wherever you are tonight, know the feeling well. The moment when something you depended on vanishes without explanation, leaving you suspended between memory and uncertainty. The team began checking their instruments as if doubt itself had become magnetic. Fiber cables were tested, antenna surfaces inspected for microscopic dust, software rolled back to earlier versions, logs combed line by line. No error revealed itself. Equipment doesn't decide to stop receiving a signal. Something out there must have stopped emitting it. Yet, nature rarely behaves in abrupt binaries. Even the death of a star comes with a gradient, a slow fading, a final flare. The sudden quiet here felt unnatural, not in a supernatural way, but in a way that suggested the cause belonged to a category not yet defined. Imagine, for a moment, standing outside in the cold night near one of those radio arrays, the metal dish towering above you like a frozen wave. The air is still, the sky enormous, and somewhere in that vastness hides the emitter that once made the graph tremble. Then came the first oddity. A researcher noticed that while the bursts had stopped, the background noise floor in that region of the sky dropped by a detectable fraction. Not a dramatic plunge, just a thin, almost respectful decline, as if the cosmos had taken a long breath in. Background radiation shouldn't do that on localized scales. It's supposed to be uniform. The thermal leftover of the early universe spread evenly across the sky. But here it slipped, making a hollow below the usual cosmic hiss. To investigate, the scientists activated older equipment stored in archives, relics of earlier missions. Detectors retired, not because they were broken, but because time had marched on technologically. Dust was wiped from lenses, cables reconnected, screens coaxed back to life with nostalgic flickers. One of these aging instruments picked up something subtle. Not a burst, not a wave, more like a shimmer in the data, a soft oscillation too delicate for newer sensors, optimized for sharp events. The shimmer wasn't a signal, but a shadow of a signal, the negative space left behind when something stops moving. Think of it like watching the imprint of a bird's wings in the air after it has flown away. Not the wings themselves, but the fading turbulence echoing in their absence. The team shifted strategies. Instead of hunting the anomaly directly, they hunted its footprint. The shimmer appeared intermittently, irregularly, sometimes too faint to be sure it wasn't another artifact, yet persistent enough that denial became harder each day. One physicist compared the oscillation to the mathematical residue left behind by a gravitational wave passing through space-time. Except gravitational waves don't simply stop and restart. They travel, they fade, but they don't hover. You can picture the researchers crowding around chalkboards and tablets, sketching curves, drawing parallels, arguing quietly about whether they were chasing a ghost or a groundbreaking discovery. The atmosphere was a mixture of exhaustion and awe, like mountaineers watching a summit shift in fog. And while the debates unfolded, a quiet shift occurred in the public-facing side of astronomy. People who never read scientific papers began asking questions online, circulating grainy images of the early bursts, speculating about extraterrestrial messages, hidden codes, or cosmic warnings. The scientists didn't fuel these theories, but they didn't extinguish them either. Because the truth was simple, they themselves didn't know what they were dealing with. Then, weeks after the silence began, a graduate student spotted something no senior researcher had thought to examine. One of the early bursts had been recorded simultaneously by a weather satellite not designed for astronomy. The signal had bounced off the satellite's sensors like a reflection hitting an unintended mirror. This accidental viewpoint revealed a faint polarization shift inside the burst, a twisting of the wave as though it had passed through a region of space warped by intense magnetic tension. Magnetic fields that strong only occur near neutron stars or black holes, but there were no neutron stars in that region of the sky, no black holes either. In fact, the area was considered cosmically quiet, a patch of darkness with no remarkable features, the astrophysical equivalent of an empty hallway where a whisper would have no reason to echo. Yet something had twisted those waves. Soon, theories branched into speculative terrain, a collapsing pocket of exotic matter, a ripple from a starquake in a star we didn't know existed. A gravitational lens-bending space in a way models had never predicted. But the most unsettling idea came from a young researcher with a habit of thinking sideways. What if the region isn't empty? She asked. What if we're seeing the edge of something invisible that doesn't behave like normal space? Her colleagues went still, not because the idea was ridiculous, but because it fit too cleanly with the data. Invisible structures aren't new to physics. Dark matter halos, filaments of cosmic web, void boundaries. The universe hides more than it reveals. But this was different. This was dynamic, reactive, almost sensitive to observation. And then came the detail that changed everything. The polarization shift increased slightly when telescopes gathered more data at once, as if the invisible structure responded to the attention. It was absurd, impossible, yet measurable. You can imagine the stunned quiet in the control room, the fluorescent lights humming softly overhead, as each scientist realized the same thing. They weren't just observing space. Something in that region might have been observing them back. And in that stillness, before fear or excitement could fully settle, another shimmer appeared, stronger than before, as though the silence itself were preparing to speak again. There is a particular quiet that settles in your mind after wandering through mysteries too large to fit inside ordinary explanations. You've traveled tonight through strange bursts, vanishing signals, impossible silences, and shimmering distortions that seem to bend under the weight of observation. As we reach the end of this journey, notice how the unknown doesn't feel threatening anymore. It feels spacious, soft like a horizon stretching farther than your worries can reach. If you imagine yourself lying there in your room, everything dark except the faint glow of your screen, you might feel the strange comfort of scale. The universe is vast, unpredictable, full of riddles even its most brilliant researchers cannot untangle, and somehow that makes your own uncertainties a little easier to hold. You don't have to solve anything tonight. You can just breathe. Throughout this story, you've stood beside scientists brushing frost off their telescopes, replaying strange crescents of data, and listening to silences heavy with implication. You've drifted through starless regions where space itself behaved like a living boundary. You've witnessed doubt become collaboration and hesitation become discovery. And all of it started with something simple, a handful of measurements no one knew how to interpret. There's a quiet beauty in that beginning, the reminder that progress often hides inside confusion. Scientists don't work in straight lines. They stumble, circle back, argue, hope, and try again. The cosmos rarely hands them answers. Instead, it gives them puzzles wrapped in noise, demanding patience rather than certainty. As you rest here now, let that patience sink into you as well. If your mind feels slow or blurred from the length of this journey, that's okay. It mirrors the way researchers felt after weeks of chasing an anomaly that refused to behave, And if you drifted off for part of it, that's even better. This space was built for that gentle release, a place where wonder and rest can exist without conflict. Before we close, notice how the opening question feels different now. When we first wondered what scientists saw and still couldn't explain, it felt like a challenge waiting for a solution. Now it feels like an invitation, a reminder that not understanding is sometimes the most honest, most human position we can take when staring into the unknown. As you settle deeper into your pillow, imagine all those observatories scattered across the world, their dishes tilted toward the sky, waiting for the next whisper from that silent region. Scientists might argue, refine models, propose daring theories, but behind all of it sits the same quiet truth. Curiosity thrives where certainty ends. And if you've enjoyed drifting through that uncertainty tonight, if this calm blend of science and mystery helped you breathe a little slower, you can gently leave a like and subscribe. It helps this little corner of the universe reach others who need a quiet place to wonder. Before you fall asleep, if you feel like sharing, tell me in the comments where you're listening from and what time it is there. It's strangely comforting to imagine people across the world, each in their own quiet room, traveling through the same story at different hours of the night. As our journey closes, let your thoughts soften. Let the unanswered questions drift into the background, no longer demanding clarity. The universe will still be mysterious tomorrow. You don't have to hold it all tonight. And as the last traces of this story fade, imagine a small light in the distance, steady, patient, waiting. Not a signal to solve, but a reminder that even in the vastness of the unknown, you are never really lost. You're part of the same cosmos that puzzles its greatest thinkers, and somehow that's enough. Sleep well, traveler. The mysteries can wait,